The modules described in this chapter provide some basic services operations for manipulation of binary data. Other operations on binary data, specifically in relation to file formats and network protocols, are described in the relevant sections. Some libraries described under text processing services also work with either ASCII compatible binary formats, for example RE, or all binary data, for example dflib. In addition, see the documentation for Python's built-in binary data types in binary sequence types, bytes, byte array, memory view. Struct interpret bytes as packed binary data. Functions and exceptions, format strings, byte order, size and alignment, format characters, examples, applications, native formats, standard formats, classes, codec registry and base classes, codec base classes, error handlers, stateless encoding and decoding, incremental encoding and decoding, incremental encoder objects, incremental decoder objects, stream encoding and decoding, stream writer objects, stream reader objects, stream reader writer objects, stream recorder objects, encoding and Unicode standard encodings, Python specific encodings, text encodings, binary transformation, text transforms, encoding.idna, internationalized domain names in applications, encodings.mbcs, Windows ANSI code page, encodings.utf8 SIG, UTF-8 codec with bomb signature. Next. Struct interpret bytes as packed binary data. Source code libstruct.py. This module converts between Python values and C structs represented at Python bytes objects. Compact format strings describe the intended conversions to or from Python values. The module's functions and objects can be used for two largely distinct applications: data exchange with external sources, files or network connections, or data transfer between the Python application and the C layer. Note: when no prefix character is given, native mode is the default. It packs or unpacks data based on the platform and compiler on which the Python interpreter was built. The result of packing a given C struct includes paired bytes, which maintain proper alignment for the C types involved. Similarly, alignment is taken into account when unpacking. In contrast, when communicating data between external sources, the programmer is responsible for defining byte ordering and padding between elements. See byte order, size, and alignment for details. Several struct functions and methods of struct take a buffer argument. This refers to objects that implement the buffer protocol and provide either a readable or read-writable buffer. The most common types used for that purpose are bytes and byte array, but many other types that can be viewed as an array of bytes implement the buffer protocol so that they can read or field without adding additional copying from a bytes object. Functional and exceptions. Functions and exceptions. The module defines the following exception and function. Exception struct.error. Exception raised on various occasions. Argument is a string describing what is wrong. Struct.pack. Format v1 v2 return a bytes object containing the values v1 v2 packed according to the format string format. The arguments must match the values required by the format exactly. Struct.pack into format buffer offset v1 v2 pack the values v1 v2 according to the format string format and write the packed bytes into the writable buffer starting at position offset. Note that offset is a required argument. Struct.unpack format buffer. Unpack from the buffer presumably packed by pack format comma according to the format string format. The result is a tuple even if it contains exactly one item. The buffer's size bytes must match the size required by the format as reflected by calcsize method. Struct.unpack underscore from format slash buffer offset is equal to 0. Unpack from buffer starting at position offset according to the Format string format. The result is a tuple even if it contains exactly one item. The buffer size in bytes starting at position offset must be at least the size required by the format as reflected by calc size. Struct.iter underscore unpack format buffer. Iteratively unpack from the buffer according to the format string format. This function returns an iterator which will read equally sized chunks from the buffer until all its contents have been consumed. The buffer size in bytes must be a multiple of the size required by the format, as reflected by calc size. Each iteration yields a tuple as specified by the format string. Struct.calcsize format. Return the size of the struct and hence of the bytes object produced by pack format, comma dot dot dot, corresponding to the format string format. Format strings. Format strings describe the data layout when packing and unpacking data. They are built up from format characters which specify the type of data being packed or unpacked. In addition, special characters control the byte order, size, alignment. Each format string consists of an optional prefix character which describes the overall properties of the data, and one or more format characters which describe the actual data values and padding. Byte order, size, and alignment. By default, C types are represented in the machine's native format and byte order and properly aligned by skipping bytes if necessary according to the rules used by the C compiler. This behavior is chosen so that the bytes of a packed struct correspond exactly to the memory layout of the corresponding C struct. Whether to use native byte ordering and padding or standard formats depends on the application. Alternatively, the first character of the format string can be used to indicate the byte order, size, and alignment of the packed data according to the following table: character, byte order, size, alignment. At the rate native equal native standard none less than little endian standard none greater than big endian standard none exclamation sign network is equal to big endian standard none. If the first character is not one of these, ampersand is assumed. Native byte order is big endian or little endian depending on the host system. For example, Intel 86, AMD 64, x86 64, and Apple M1 are little endian. IBM Z and many legacy architectures are big endian. Use sys.byteorder to check the endianness of your system. Native size and alignment are determined using the C compiler size of expression. This is always combined with native byte order. Standard size depends only on the format character. See the table in the format character section. Note the difference between at the rate and equal. Both use native byte order, but the size and alignment of the latter is standardized. The form exclamation represents the network byte order, which is always big endian as defined in IETF RFC 1700. There is no way to indicate non-native byte order. Force byte swapping. Use the appropriate choice of less than or greater than. Notes. Padding is only automatically added between successive structure members. No padding is added at the beginning or end of the encoded struct. No padding is added when using non-native size and alignment. Example with less than, greater than, equal, and exclamation. To align the end of a structure to the alignment requirement of a particular type and the format with the code for that type with a repeat count is equal to 0. See examples. Examples. Okay, it's in the same file. We will see it later in the following sections. Format characters. Format characters have the following meaning. The conversion between C and Python values should be obvious given their types. The standard size column refers to the size of the packed value in bytes. When using standard size, that is when the format string starts with one of less than or greater than exclamation equal. When using native size, the size of the packed value is platform dependent. Format C type, Python type, standard size notes. X padded byte, no value 7. C char bytes of length 1 1. B signed char integer 1. B unsigned char integer. Question mark underscore bull h short integer h capital H unsigned short integer I integer capital I unsigned integer L long integer capital L unsigned long integer Q long integer capital Q unsigned long integer N S size underscore T integer capital N size underscore T integer E 6 float F float D double float S char array bytes P char array bytes P void pointer integer. Notes: the question mark conversion code corresponds the underscore bool type defined by C99. If this type is not available, it is simulated using a char. In standard mode, it is always represented by 1 byte. When attempting to pack a non-integer using any of the integer conversion codes, if the if the non-integer has an index method, then that method is called to convert the argument to an integer before packing. The N and N conversion codes are only available for the native size selected as the default or with the M percent at the rate byte order character. For the standard size, you can use whichever of the other integer formats fits your application. For the F, D, and E conversion codes, the packed representation uses the IEEE 754 binary 32, binary 64, or binary 16 format for F, D, or E respectively, regardless of the floating point format used by the platform. The capital P format character is only available for the native byte ordering, selected as the default or with the M at the rate byte order character. The byte order character equal chooses to use little or big endian ordering based on the host system. The struct module does not interpret this as native ordering, so the P format is not available. The IEEE 754 binary 16 half precision type was introduced in the 2008 revision of IEEE 754 standard. It has a sign bit, a 5-bit exponent, and 11-bit precision with 10 bits explicitly stored and can represent numbers between approximately 6.1 E to 05 and 6.5 E plus 04 at full precision. This type is not widely supported by C compilers on a typical machine. An unsigned sort can be used for storage, but not for math operations. See the Wikipedia page for half precision floating point format for more information. When packing X inserts one null byte, the P format character encodes a Pascal string, meaning a short variable length string stored in a fixed number of bytes given by the count. The first byte stored in the length of the string or 255, whichever is smaller. The bytes of the string follow. If the string passed into pack is too long, longer than the count minus 1, only the leading count 1 bytes of the string are stored. If the string is shorter than count minus 1, it is padded with null bytes so that exactly count bytes in all are used. Note that for unpack, the P format character consumes count bytes, but that the string returned can never contain more than 255 bytes. For the S format character, the count is interpreted as the length of the byte, not a repeat count like for the other format characters. For example, 10S means a single 10 byte string mapping to or from a single Python byte string, while 10C means 10 separate 1 byte character elements. Example CC 10 times mapping to or from 10 different Python bytes object. See examples for a concrete demonstration of difference. If a count is not given, it defaults to 1. For packing, the string is truncated or padded with null bytes as appropriate to make it fit. For unpacking, the resulting byte object always has exactly the specified number of bytes. As a special case, zeros means a single empty string, while 0C means 0 characters. A format character may be preceded by an integral repeat count. For example, the format string 4H means exactly the same as HHHH. White space characters between formats are ignored. A count and its format must not contain white space though. When packing a value X using one of the integer formats B capital B H capital H I capital I, L capital L, Q capital Q. If X is outside the valid range for the format, then struct.error is raised. For the question mark format character, the return value is either true or false. When packing, the truth value of the argument object is used. Either 0 or 1 in the native or standard bool representation will be packed. Any non-zero value will be true when unpacking. Examples: native byte order examples designated by the at the rate format prefix or lack of any prefix character may not match where what the reader's machine produces as the depends on the platform and compiler. Pack and unpack integers of three different sizes using big endian ordering. From struct item 3 struct import start pack big endian bh1123 123 unpack bhl b 123 calc size bhl 7. Attempt to pack an integer which is too large for the defined field. Pack integer big endian 99999. H format requires -3276 set less than equal to number less than equal to 32767. Demonstrates the difference between S and C format characters. Pack at the rate CCC B1 B2 byte 3 B byte 1 to 3. Pack at the rate 3S B1 to 3. Unpacked fields can be named by assigning them to variables or by wrapping the result in a named tuple. Record is equal to B Raymond. Name serial school grade level is equal to record. From collections import named tuple. Student is equal to named tuple student name serial grade level. Student dot make unpack less than 10 as HHB record. Student name B Raymond serial number 4658 school 264 grade level 8. The ordering of format characters may have an impact on size in native since padding is implicit. In standard mode, the user is responsible for inserting any desired padding. Note in the first pack call below that 3 null bytes were added after the packed hash to align the following integer on a 4 byte boundary. In this example, the output was produced on a little endian machine. Pack ci at the rate ci b hash this. Pack at the rate ci 0xx b hash. Calc size ci 8 byte. Calc size at the red IC 5. The following format LLH0L results in 2 paired bytes being added at the end, assuming the platform's longs are aligned on 4 byte boundaries. Pack at the rate let's import from struct import star now pack. Right, see also module array packed binary storage for homogeneous data, module json encoder and decoder, module pickle python object serialization. Application, so array json pickle. Applications, two main applications for the struct module exist: data interchange between python and c within an application, or another application compiled using the same compiler native formats, and data interchange between applications using agreed upon data layout standard formats. Generally speaking, the format strings constructed for these two domains are distinct. Native formats, when constructing format strings which mimic native layouts, the compiler and machine architecture determine byte ordering and padding. In such cases, the format character should be used to specify native byte ordering and data sizes. Internal pad bytes are normally inserted automatically. It is possible that a zero repeat format code will be needed at the end of a format string to round up to the character byte boundaries for proper alignment of consecutive chunks of data. Consider these two simple examples on a 64-bit little endian machine. Calc at the rate LHL 24 byte, calc at the rate LLH 18. Data is not padded to an 8 byte boundary at the end of the second format string without the use of string extra padding. A zero repeat format code solves that problem. Calc at the rate LLH0L, it's 24. The X format code can be used to specify the repeat, but for native format it is better to use a zero repeat format like 0L. By default, native byte ordering and alignment is used, but it is better to be explicit and use the prefix character. Standard formats, when exchanging data beyond your process such as networking or storage, be precise. Specify the exact byte order, size and alignment. Do not assume they match the native order of a particular machine. For example, network byte order is big endian, while many popular CPUs are little endian. By defining this explicitly, the user need to not care about the specifics of the platform their bytecode is running on. The first character should typically be less than or greater than or exclamation. Padding is the responsibility of the programmer. The zero repeat format character won't work. Instead, the user must explicitly add X pad bytes where needed. Revisiting the examples from the previous section, we have calc size less than QH6XQ, peg less than QH6HQ123 equal to pack at the rate LHL123 is equal to true. Calc size LLH 18, pack at the rate LLH123 equal to pack less than QQH123 true. Calculate QQH6X calculate size at the rate LLH0124 pack at the rate LLH01123 true. The above results executed on 64 machine aren't guaranteed to match when executed on different machine. For example, the examples below were executed on a 32-bit machine. Classes, struct module. The struct module also defines the following byte: struct.struct format. Return a new struct object which writes and reads binary data according to the format string format, creating A struct object once and calling its methods is more efficient than calling module level functions with the same format, since the format string is only compiled once. Note: the compiled version of the most recent format strings passed to the module level functions are cached. So programs that use only a few format strings need not worry about reusing a single struct instance. Compiled struct objects support the following methods and attributes: pack v1 v2 dot 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 identical to pack function using the compiled format. Len result will equal size. Pack into buffer offset v1 v2 dot 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 identical to pack into function using the compiled format. Unpack buffer identical to unpack function using the compiled format. The buffer size in bytes must equal size. Unpack from buffer 0 identical to unpack from using the compiled format. The buffer size in bytes starting at position offset must be at least size. ITER unpack buffer identical to iterator unpack function using the compiled format. The buffer size in bytes must be a multiple of size. Format: the format string used to construct this struct object. Size: the calculated size of the struct and hence of the bytes object produced by pack method corresponding to format.